Ladies and gentlemen, welcome to machine learning. In this video, we will have a look at the geometric interpretation of our solution of the linear least squares. Let's jump right in. So in the last videos, we talked about how we can get the weights of our parameters, of our basis functions, so that we minimize the error. Now we want to have a look, well, how can we interpret that in a geometric way? So let's say we had our observations x and y, where we had x is 1, 2, and 3, and y is our, for example, 3, 7, and 9. Then we proposed a function where we had x, or our function f of x is equal to some weight or bias plus our w1 times x squared. And we, after getting the linear least square solution, we could propose that omega 0 was then equal to 0.3 and omega 1 is equal to 0.9. So this was the solution we got from the linear least squares. Now we can say, well, how does it actually look like? So if we say that our solutions, so our observed values are y from y1 to yn are these values. So it's 3, 7, and 9. And these are now our basis function that we chose in the design matrix. Let's have a look at our design matrix. The design matrix was this one. So it's what is happening with our x's if we insert them in our basis functions. So here we have our phi 0. This is always our dummy basis function. So this is a 1, 1, and 1 because we have n observation. This goes for each observation. We have 3 of those. And this is our phi. So this is our x squared. So phi 1 was x squared. So this would be 9. 7 squared and 9 squared, say 3 squared, because this is our function. And then we then we got our weights, and those weights basically define another vector. So we can think of phi 1 and phi 0 as vectors that are in the plane, or that define a plane M, and the projection of our design matrix with our weights is basically the projection of our actual true values into the plane of M. So this was the original, and we projected downwards onto the plane that we can define with those two vectors, so with our basis functions. And we see that we have a projection matrix where we project the true into our plane, and we see that we have a error vector, which is y minus the projected vector. So it's this vector minus this vector, and this is basically, again, a projection matrix M that projects our true values, or that projects our true values into a new vector that is the error vector. And we see that, first of all, if we really chose the most optimal values, the projected error, so the error of the true function of the true vector that we try to find onto that plane, this error vector is orthogonal to our phi 1 and phi 0. So from the design matrix, this one goes here, and this one goes here. This is just the three-dimensional case, so we can basically plot it. So we see that we have projection matrices, and if we choose the values that they are optimal, we will get a orthogonal projection. So we assume that for now we have much more observation that we have basis functions. So M is now a subspace of n. So we have many more of those n's than we have our basis functions, M. So we have our error vector, the error vector, which is basically just the difference between the true and the observed ones. And it's perpendicular to the subspace of M and is orthogonal. Then we say that we can design a hat matrix. This is our hat matrix because we're saying that it simply puts a hat onto our y's. So this is the projection of our true y's onto our predicted y's, so y hats. So it's the projection matrix or the hat matrix. Then we have another matrix. This is the M matrix. It's also a projection matrix, but it projects the true vector of y into our error vector. So this is how you can see that or interpret the results. So let's remove all this to get a better view. So we see that if we have the optimal solution, we can actually, with these two vectors, build a plane that includes this vector. If we do that, the error of our predicted values is actually 0, and we have the best possible values that pass through every possible data point. So every possible data point is perfectly on that line that we got with the help of those parameters. But this is mostly not the case, but you can interpret that we want to minimize this distance from that point to that point. This is our projection into the space that we built with our basis function, and this is our actual true vector, and we want to get this distance as minimal as possible. I hope this video gave you a better understanding into the geometric interpretation of the linear least squares results that we got from the basis functions. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.